The oscillograph has recorded 69 kV bus voltages in all three phases: neutral current in a grounding transformer and current in the bus tie breaker, all three phases as well as the residual current. The total elapsed time between the initial fault and final breaker clearing was 65 cycles, just over 1 second. Notice that we have broken the traces to indicate where the waveforms just repeat themselves. After 3 cycles of pre-fault recording, we see the onset of a single line-to-ground fault. This fault was actually caused by a tree falling across one of the phase conductors. The tree provides a path to ground. Looking at the oscillogram, the transformer neutral current and the tie breaker residual current both clearly show that the fault is line to ground. The high C-phase current in the tie breaker and the low C-phase bus voltage tell us which phase has been faulted. The single line-to-ground fault endures for 25 cycles. At this point, the C-phase conductor burns open, allowing the tree to fall onto A phase. However, the tree still maintains contact with C phase. Now, the nature of the fault has changed to a double line-to-ground fault. Over the next 5 cycles, you can see the effect of the two-phase fault. Both A phase and C phase currents in the tie breaker rise sharply. Both A phase and C phase bus voltages are depressed. Transformer neutral current and tie breaker residual current are both still present, but they are reduced in magnitude. This is because a double line-to-ground fault is more balanced than a single line-to-ground fault. At this point, breaker Y finally trips to clear one end of the faulted line. The tripping occurs 30 cycles after the initial line-to-ground fault started. This is reasonable since we are dealing with a high impedance fault. Thus, the level of fault current is low, resulting in a relatively long operating time. For the next 25 cycles, we still have a double line-to-ground fault, but the current magnitudes are very much reduced because one end of the line is open. You can see that the A and C phase bus voltages are back to near normal. At this point, the fault again changes. The A phase conductor now burns open. The tree contacts B phase and falls to the ground. But all 3 open conductors are now in contact with ground, resulting in a 3-phase to ground fault. For the next 10 cycles, we have a balanced 3-phase fault. You can see this from the 3 fault currents in the tie breaker and the fact that neutral and residual currents are now 0. Breaker Z at the other end of the faulted line now trips to completely clear the fault. This occurs 35 cycles after breaker Y trips. Again, this is reasonable because the fault current is low and also because the fault is in zone 2 of breaker Z's protection. Thus, tripping is further delayed. This example has demonstrated 2 things. First, the nature of a fault can change during a disturbance, and in this case, the protection operated correctly to clear the fault. Secondly, our examples showed that recording equipment located several buses away from the actual fault can still provide valuable information during a fault investigation. Let's now move on to our third case, an overtrip for a remote fault. This is a clear example of misoperation. Breaker A at 115 kV substation Z trips for a remote fault on the 230 kV system. With the help of the oscillographs located in substation X, we were able to spot the problem and correct it. In substation X, the oscillograms monitor the transformer breaker's A phase current and the 0 sequence residual current. Also monitored are the 115 kV bus voltages in all 3 phases, as well as A phase and residual current for breaker B connecting to substation Z. You can see the onset of a single line-to-ground fault on the 230 kV line. The fault was on A phase, as shown by the sharp increase in A phase current through the transformer breaker and breaker B, and also by the depressed A phase bus voltage. The presence of zero sequence in the breakers also indicates a ground fault. Tripping on the 230 kV system was correct, and the fault was cleared in just over 3 cycles. But look at the phase current through breaker B. Normal load current flows after the 230 kV fault clears, but 5 cycles later, breaker A trips at the remote end of the line. The incoming feed from substation Z is now interrupted. After 14 cycles, breaker A recloses and remains closed. Further investigation revealed that while the fault was on, breaker A received the proper carrier blocking signal. But this signal was removed too quickly. As a result, the relays at breaker A saw fault current as well as a green light to trip. The problem was solved by resetting the timing of the carrier block signals. Again, this is a case where the over-trip problem may have gone unnoticed if we had not checked the oscillograms. Okay, let's take a break now, and then we'll come back and describe some more examples. In the meantime, switch off the videotape and review your written materials. Hello. In this last segment, we'll examine some additional oscillograms from actual case histories. These cases demonstrate how recordings can be used to assess the performance of major system equipment, such as circuit breakers, transformers, and generators. Let's begin with case 4, a breaker restrike. By way of review, you know that when a circuit breaker opens to interrupt current, an arc is formed between the parting contacts. Normally, this arc is quickly extinguished by the dielectric in the interrupting chamber, which may be air, gas, oil, or vacuum. After the arc is extinguished, there is voltage buildup across the open contacts. If this voltage builds up too fast, or if there is a sudden surge of voltage, the dielectric strength of the breaker's insulation could be exceeded. When this happens, the arc is reestablished and current again flows. This dielectric breakdown is known as a restrike. It can cause serious damage to the breaker contacts, in addition to deterioration of the oil or gas dielectric. But how can this happen? Well, here's one way. A lightning strike to a phase conductor flashes over an insulator, causing a single line-to-ground fault.